The record for the deepest human dive into space was set by accident. In April 1970, the crew of Apollo 13 reached a distance of 400,171 kilometers away from Earth. That distance was forced by a catastrophic engine failure. Their only option for survival was to loop entirely around the back of the moon to catch a ride home. Now, a new crew of 4 astronauts, including pilot Victor Glover, is preparing to fly the Artemis 2 mission. They will be the first humans to intentionally push past that 50-year-old limit. The physical stakes at this distance are absolute. If the Orion spacecraft engines fail without a backup plan, the crew would remain stranded in deep space. To make this mission survivable, engineers rely on a specific orbital maneuver called the free return trajectory. This map shows how it works. Mission Control aims the spacecraft slightly ahead of the moon, catching its gravitational pull. The moon's gravity acts like a slingshot, whipping the spacecraft around the far side and accelerating it back toward Earth without a single engine burn. This flight path provides a predictable, physics-based safety net that guarantees a return trip even if the spacecraft's power systems fail. To use the gravitational slingshot, the spacecraft must fly over the far side of the moon, a place often mistakenly called the dark side. The actual physics is a concept called tidal locking. The time it takes the moon to rotate once on its axis exactly matches the time it takes to orbit Earth. Because those speeds are perfectly synced, the hidden side of the moon receives just as much sunlight as the side we see. It is simply permanently obstructed from our view. That massive solid rock creates a physical barrier blocking all telemetry between the spacecraft and Earth. The moment the Orion capsule slips behind the lunar mass, every radio, internet, and communication signal is severed for exactly 40 minutes. During this blackout, Mission Control in Houston is unable to track the ship or assist the crew if an emergency occurs. While cut off from Earth, the astronauts look out the window at a landscape with features rarely seen from our home planet. The dark, smooth basaltic plains, the seas that form the familiar patterns on the moon's near side, are completely absent here. This cross-section shows the geological cause. The crust on the far side of the moon is significantly thicker than the side facing Earth. That thickness prevented ancient lava from bleeding out and smoothing over impact sites, preserving billions of years of asteroid strikes. We see the results in features like the Oriental Basin, a massive multi-ring impact structure that remains largely uncovered by lava. In these 40 minutes, the crew observes an untouched, pristine record of the early solar system's violent formation. The isolation also provides a rare astronomical vantage point. The crew witnesses a solar eclipse, perfectly clear and undistorted by Earth's atmosphere. As the ship travels deeper into the moon's shadow, they watch an Earthset, the blue marble of our world sinking entirely below the lunar horizon. As the spacecraft completes its arc, the Earth reappears. This Earthrise signals the end of the 40-minute blackout. Witnessing these orbital vistas serves as the psychological and scientific reward for surviving the deepest physical isolation in human history. The final phase of the free return trajectory drops the capsule back through the atmosphere, returning safely with a splashdown in the Pacific Ocean. Successfully executing this flight path sets the stage for the Artemis 3 mission. While the Apollo missions were designed to reach the surface and return, the modern objective is to learn how to establish a long-term human presence on the moon. Executing this mission confirms that our safety systems and orbital math are reliable enough to support the next step, a sustained return to the lunar surface.